in unidirectional. Okay. So what do we mean by unidirectional? Okay. So the most commonly used is tensile. Okay. That's why for all the material over here you see, right? For all the material you see in tension, everyone has properties. All of them have properties. Even in the yield, all of them have what? Properties. Okay. So why? Because it's the cheapest. It's easy to set up. Okay. Why most commonly used? It is cheap, repeatable. Okay. That's why we use it. So in tension, okay, so if you have a specimen over here, okay, I'm going to draw the centroid. Okay, so this is our centroid, and this is how our load are applied. Okay, P and P prime. Okay, so that is in tension, and then the next one we use is compression test. Okay, so it's just pure compression. Like the one on top is in tension, the one at the bottom that I'm drawing now is in compression. So again, this is our centroid. Okay, and then this is under compression. Okay, so the test can be a stretching test or pushing in test, and then the last one is a torsion test or shear test. Okay, so in shear, what we tend to do is we will have them in so now the stresses applied and is in this direction. So this is T. So T represent torsion. Okay. So you either do them in tensile, compression, or in shear. You don't combine them. Okay. Combining them, the setup get more complicated and it's more difficult to do. Okay. So these are the most commonly used one, and the most popular one because it's cheap, has good repeatability, is the tensile test. Okay, so next I'm going to introduce you to an element. Okay, so an element is basically a strain gauge put on the surface of our structure. Okay, so all these are known as our element. Physically, they are your strain gauges. So strain gauge are sensors that they are able to relate displacement to stresses. Okay, so that's what we call strain gauge. So all these are all your elements. So the elements are loaded differently. Okay, so I'm going to use a common transformation. So I'm going to call this my X. This direction is your Y, and this direction is your Z for all of them. We're going to use the same transformation. So now we draw the element. Okay, we sketch out the element. So this is the element. So all of them has element. Okay, so this is element. Okay, and then the last one also has element. So part of the course that you will go through is to determine the stresses on the element. So for this case, it's straightforward. Okay, so you know that this is under tensile. So this is your stress X. Okay, it's pulling outwards, it's tensile. The load is pushing inwards. This is what we call compression. And then when you have shear, right, this is how the structure is loaded in shear. Okay, so this is shear XY, that is your shear YX, and the shear XY is equal to shear YX. Later on, I'll tell you why when we touch learning Mohs circle. Okay, so that is our element. So why am I showing you this? Okay, what is the purpose of showing you the elements? Okay, so from the elements, okay, you are going to learn Mohs circle. Okay, from the elements, you are going to construct Mohs circle. Okay, so Mohs circle for this case in the state for introduction, I'll just sketch 2D. Okay, later on you will learn 3D Mohs circle. In reality, you're going to construct 3D Mohs circle. Okay, so how does this look like? Right. So if we were to draw Mohs circle for this, so on Mohs circle, this is your normal stress, and on the y-axis, this is your shearing stress. Element rotate clockwise, element rotate anti-clockwise. Okay, some of you will remember this. So I usually like, because of the transformation over here, this is your X and this is your Y, and this is for all of them. You will see that I will call this point or this surface, the point is point X. Over here is point Y. So we realize that point X has its tension. So this is point X, right? Y is 0. This is your point Y. They have 0 shear. And then this is your Mohs circle. Okay, so this is your Mohs circle. Your 2D Mohs circle for now. Okay. And I like to highlight to you over here, this point is known as your stress 1. These points are known as your stress 2. So stress 1 and 2 are known as your principal stress. Okay, principal stresses. Okay, so that is your Mohs circle in tension. And then if you look at in compression, how does it look like? So I'm going to sketch for you also. So this is our Mohs circle. So this is our, all of a sudden my mouse go on strike. I can't see my mouse now. Hey. Oh, I can see my mouse. I thought my mouse went missing. So I'm going to draw 2 axes again. Normal stress. Okay. So this is your normal stress. This is your shear stress. Element rotate clockwise. Element rotate anti-clockwise. Don't worry about those yet. Okay, this is just an introduction. So if I were to call this point X, and if I were to call this point Y, right? And we realize that now it's under compression. So this is your point X. Over here, this is point Y, and we have 0 shear, and then this is your Mohs circle now. Okay. Okay, so this is your mole circle, and I think I'm going to move this out a bit. My bad. You know what? Okay, so this over here is your point X. Okay, so again over here we can label this 0.2 or 0.1 or stress 1, and this is your stress 2, right? You can go either way. Stress 1 and 2, it's not necessary stress 1 have to be on the left hand side, stress 2 is on the right hand side. No. Okay, it's how you, whatever you want to, how you want to name them, does not matter. Okay, and then the third one is the structure or the elements has zero normal stress, it has shearing stress. Okay, so you have normal stress over here, and then you have shearing stress over here. Right, element rotate clockwise, element rotate anti-clockwise. This is your point X, and over here is your point Y. And if we were to put our finger in the center, and if you were to see how this arrow is rotating the element, is generating a anti-clockwise rotation, the yellow arrow, right? It's generating anti-clockwise rotation. So over here, this will be your point X. Okay. Over here, this will be your point X, right? Because over here, it shows anti-clockwise. And then on the blue highlight at point Y, it's going to generate a clockwise rotation. Okay, so this is your point blue, clockwise rotation. So that is over here. Okay, so over here, this is your point Y. And then from here, again, you can construct your mole circle. So from your mole circle, right, you can determine stress 1 and you can determine stress 2. Okay, so I keep on highlighting this stress 1 and stress 2 for a certain reason. Later on, you will understand why. Okay, so what we see down here is all these values. Okay, so these are all your all how they get their material, how they test the material. They find what the stresses are on the element, and they construct mole circle. Okay, now this is easy. Okay, now what I'm trying to say is this: all this value that you see over here, right? They are all your principal stress. Okay, for tension, these are all your principal stress. Your shearing stress is your maximum shear stress. Okay, now I want to focus just on the U. Okay, because we know that usually when we design material in the ductile region, it's usually the U strength. Okay, and I'll make a statement regarding the factor of safety, right? If you were to use stress U over stress allowable, right, for the brittle, the value is not going to be any difference, right? Because the U and ultimate are very similar. So I think it's safe to say, as structural engineers or mechanical engineers like all of us, it is safe to use the U rather than to use the ultimate. Okay. So we can see that all this property has been listed, especially in tension, right? They are all in its principal stress. Okay, and then in shear is your tau max. What do I mean by tau max? If you look at mole circle, where is tau max? Okay, so I'm going to draw a horizontal line. Okay, so you can see that this value over here, from here to here, this is your tau max, right? And then likewise from here to here. Okay. These are your tau max. And then the shear